Now we're going to have a look at the first presentation, and we're going to hear about reference scenarios and traffic spaces. For this topic, we have three speakers. The first one is Stefan Berger. He is physicist at the Opel Automotive GmbH, and there he is the senior project lead for advanced driver assistance systems and automated driving. Within the Z-level project, he's the Opel project lead, and he's the leader of the work package for traffic spaces. Our second speaker, Andreas Pütz, he's from the Fortwerke GmbH, and he's a research engineer at Automated Driving Europe. And he is member of the work package 1.2 at the Z-level project, and he is responsible for reference scenarios. And last but not least, we have Daniel Becker. He's a research associate at the RWTH University at Aachen, and he is for the Z-level project involved in model development of traffic agent and static environment. So Stefan, Andreas, Daniel, very welcome to stream number 2. And for the first part, I hand over to Stefan Berger. So Stefan, please take over and the stage is yours.
Thank you, Matthias, and good afternoon to everybody. So let's first have a quick look on the agenda for this session. Next chart, yeah. I will begin with a short motivation and the introduction about scenario description and traffic spaces. Andreas Pütz will then follow with his presentation on reference scenarios, and Daniel Becker will conclude our session with demonstrating a tool for the generation of roadmaps. So first, I would like to recap one of the principal goals of the Z-level project. This is to build up a simulation environment, to test and validate automated driving functions, to test and validate vehicle components, for instance, environmental sensors, or to identify critical scenarios. So this is a very complex task. Therefore, we took a stepwise approach and developed several traffic spaces from simple to complex. But how did we do this? The definition of traffic spaces and scenarios is essential for every traffic simulation, and the proper choice of traffic space and scenario for your simulation run will directly influence the results of your simulation. For the scenario description, Z-level takes profit from the so-called 6-layer model, worked out within the public funding project Pegasus. In the following slides, we will go through the different layers in detail. Layer 1 gives a description of the road geometry. That is, for instance, the number of lanes, the lane width, road curvature, lane marks, and so on. Layer 2 contains the so-called road furniture and traffic rules. This comprises side rails, trees, buildings, but also traffic signs and traffic lights, and hence determines the rules for the behavior of the traffic participants. Layer 3 can describe temporary modifications or events. This might be a road construction or a construction vehicle, closed lanes or closed roads. The layers 1 to 3 describe the static part of the scene, also called traffic space for the simulation. In layer 4, now moving objects are added to the scene. This comprises all traffic participants like passenger cars, trucks and buses, motorbikes, cyclists and pedestrians, but it may also include animals, even a football rolling across the street. In layer 5, environmental conditions are being described. Rainfall, snow and ice, fog, lighting conditions. And finally, layer 6 provides digital information available, as for instance, mobile communication services or vehicle-to-infrastructure communication. The layers 4 to 6 describe the dynamic part of the scenario. And now I'm going to show you the various traffic spaces we have developed within the project. Traffic space 0 is a very simple one, a straight road with one lane and a sidewalk in each direction. This traffic space can be used for the testing and for testing the interaction of different components of the simulation tool. For instance, to check whether an open drive map can be loaded into the simulation tool, or to check the interface to a pedestrian model, or to verify that the automated driving function reacts to crossing pedestrians. Traffic space 1 shows an arterial road with a merging lane. This is slightly more complex and allows to simulate merging scenarios with lane changes, acceleration or braking actions, and this helps to build up and optimize your simulation environment. Traffic space 2 shows a simple four-way intersection with one lane in each direction. Giveaway and right-of-way signs provide the traffic rules, and pedestrian crossings allow to simulate an interaction between different kinds of traffic participants. Within set level, the simulation use cases used this traffic space to build up their simulation for project milestone 2, end of February this year. Traffic space 3 is represented by an open drive map of the so-called research intersection in Braunschweig in Germany. It has numerous lanes, traffic lights, pedestrian crossings and bicycle lanes. This traffic space allows to apply very complex scenarios with many interactions of a variety of traffic participants. This challenging traffic space will be the baseline for scenarios to be run in simulations at milestone 3, close to the end of the project in 2022. And now I would like to hand over to Andreas Pütz and his presentation on reference scenarios.
Thank you, Stefan. As it was mentioned in the beginning of the presentation, the scenario description in set level is structured into static elements that we call traffic spaces and the dynamic elements that we call reference scenario. After Stefan has shown you the static elements of the scenario, I would like now to add the dynamic elements to the scenario. In case of the simplest scenario on the straight road, there are two vehicles and two pedestrians that are about to cross the road. All traffic participants in the scenario are controlled by traffic agents, meaning that there is no real ego vehicle in this scenario. One of the pedestrian agents is not considering the approaching vehicles and will cross the road so that the approaching vehicle has to react on its behavior. The other pedestrian notices the approaching vehicles and adjusts its crossing intention with regard to the current situation. The second scenario is also still pretty simple. On the arterial road Stefan has described before, two vehicles drive behind each other, forcing the ego vehicle on the merging lane to decide whether it wants to merge in front of the first traffic vehicle, between the two vehicles, or after the second vehicle. This means that this is also the first scenario in which we have a predefined ego vehicle and that the behavior of the related automated driving function can be analyzed. In addition, the criticality of the scenario could also be investigated by varying different parameters of the scenario. Maybe a more interesting scenario is a reference scenario 2. The simple rectangular intersection was crowded with various traffic participants. The ego vehicle you see here in blue intends to turn right and has therefore to consider especially the pedestrians that are crossing the arm of the intersection it is about to enter. By doing so, the line of sight of the ego into the arm of the intersection is blocked by a parked vehicle on the right-hand side. As Stefan explained in the beginning, this scenario shows an increased level of complexity as it could also occur in a crowded urban environment. Therefore, this scenario was used in the efforts for milestone 2, which was recently finished. Due to the fact that this scenario is the most complex that was used in set level so far, I integrated a short video of the scenario. You will see the progress of the scenario from the ego perspective. So the ego is a white car in the foreground. The implemented automated driving system conducts a right turn and therefore has to adjust its lateral and longitudinal trajectory based on the behavior of the numerous other traffic participants in the scenario. A short outlook on what we can expect from the remaining project duration. For milestone 3, we will again increase the complexity of the scenario on the 2 levels. The first one is that the traffic space becomes more challenging with an increased number of lanes and so on. At the same time, the driving demand of the performed driving maneuver for the automated driving system will increase. So the task is to perform a left turn with oncoming traffic on this complex intersection. Maybe we will also integrate again some side occlusions into the scenario, but that has to be decided in the progress of the upcoming development in the simulation use cases. Before I will hand over to Daniel for showing a tool that can vary the traffic spaces for these scenarios, I would like to mention that all traffic spaces and scenarios are provided with a Creative Commons license. This license allows free usage of the provided OpenDrive and OpenScenario files, meaning that if you are interested in using these scenarios, you can download them from the set level homepage after the event. With that, I hand over to Daniel for the next part.
Thank you, Andreas. Earlier in the session, we learned about the 6-layer model, which is the basis for the following considerations. Often, the generation of road networks is a manual and time-consuming task. Therefore, in the context of set level, we try to conceptualize a format that makes it easier to describe road networks in a straightforward way and implemented a tool that generates a standard map format. Concrete scenarios can be described with open standards like OpenDrive and OpenScenario, as we learned, since lots of research has been done in the context of layer 4, where dynamic objects are considered. We will focus on layer 1. The goal is to have a more logical description of a road network than OpenDrive offers. The main requirements are that the format should be non-redundant, easy to vary, it should be a modular approach, and be orientated on real road constructions, so we use only spirals, arcs, and lines as geometric primitives. Those considerations result in a format that can be visualized as a tree and is stored in XML format. The road network consists of various segments which are defined in their own coordinate systems. Then those segments can be combined to form a road network. In addition, loose ends of segments can be closed automatically with a close road network tag. In the following, let's have a closer look on how to build those segments, starting with a road. Roads are described similar as in OpenDrive, but are defined curvature continuous. So we've got no redundancies after each geometric primitive. So a start point, a start orientation, in addition to the curvature of a distance graph, is sufficient to define a distinct curve without degrees of freedom. To illustrate the concept for junctions, let's have a look at a simple example. An X junction should be defined. Therefore, 2 distinct roads are required. Both are constructed in their own local coordinate systems, in this case 2 straight lines, but a concatenation of lines, spirals, and arcs would be possible as well. To create a junction from these 2 reference lines, an intersection coupler is needed. In this tag of the input format, we define an intersection point along S, which is along the reference line, and then a reference coordinate system which is chosen and the angle under which the roads intersect is set. Now we've got a junction on reference line basis, and the next step is to generate lanes and connection roads. The first step here is to cut free the intersection area, which means from the intersecting point going a given distance in each junction arm. The new reference lines are stored internally. The next step is to generate the lanes of in and outgoing roads. They can be different lane widths, of course. We stored main and access roads predefined, which differ in lane widths and the number of lanes. The third step is to calculate the connection roads inside the intersection. At this point, we are only angle continuous because at this slow speeds, it's sufficient. If nothing else is specified, every possible transition is generated. And finally, all the lanes are added to those connection roads. If source and end lane have different widths, that's not a problem. There will be no jumps. It will be automatically generated. Now we are able to describe and generate single intersections and roads. To form a complex road network from these segments, we can combine them by connecting their ends. First, the reference element is chosen and its position and orientation in the global frame is fixed. Then for each combination of segments, the two ends of the respective segments are defined. Since we demand right now that the curvature is 0 at start and end of each segment, it's sufficient to specify both connection ends and we have an unambiguous connection. That way, we can continue to assemble junctions and connection roads to form a complex road network. Eventually, at some point, we end up with two ends that shall be close the road network. This connection can be automatically generated with help of a small optimization problem, which is required since it's not possible to directly calculate the matching parameters for a spiral. So now we would theoretically be able to perform endurance runs on this map. Now let us have a look at an example. The displayed figure shows the two T-junctions that are connected at the red X. What I want to show with these two junctions is the ease of use of the road generation tool. Both junctions are almost defined the same. Only the arc's curvature of the respective main roads differs in sign and magnitude. The upper two junction has a flag activated that generates an additional left turn on the main road, as you see here. That means if one would like to change the appearance of a road network, only small changes, in this case 2 numbers, have to be done. The resulting junction in OpenDrive differs at hundreds of lines in the XML file. Also, the format is easier to maintain since there are only 47 lines of code compared to the 937 of the OpenDrive file. A second example shows a more complex road network generated with the presented tool. It consists of 3 intersections, 1 roundabout, a manual connection road, and 4 automatically generated closed-node road network sections. Sorry. Again, the number of lines of code is much smaller than in the resulting OpenDrive file. Additionally, we imported this map in IPG CarMaker and tested if vehicles can drive through the road network in a simulation which works. So in the previous slides, we saw an approach to describe and generate road networks in a non-redundant, rather straightforward way. This allows us to take the next step and think about a concept to vary those road networks. As of today, lots of research has been done regarding the 4th layer of the introduced 6-layer model. Road users are placed in different places with different initial conditions or trajectories. However, it might be possible that the road network, in this case layer 1, also challenges the vehicle under test. 2 questions arise, for example. Which properties of a road network are relevant for an AD function and how can that be shown? In order to answer those questions, the first step is to analyze real road networks and extract parameters or key performance indicators that can be used to parameterize a simulated road network. Because once we can say, now we've got a synthetic road network that corresponds to realistic ones, it is possible to start performing test runs with varied road networks and analyze how that may affect the safety of an AD function. So at the example of the city of Berlin, we analyzed junctions in here HD maps. I will show some of the results on this slide that shall show how these parameters might be used in the road generation tool. First, we've got the mean widths of lanes that are on the junctions. It is noticeable that there is a peak around 3.5 or 3.6 meters, which seems plausible for inner city junctions, and aligns with the road construction rules. Next, we have a look at the so-called intersection area I mentioned. we define that this is the distance from the intersection point of the reference lines to the start of possible turning lanes. Again, we see a peak at a distance that seems realistic for medium to small intersections. Another interesting measure might be the intersecting angle of junctions. In this case, the angles between the three arms of T-junctions are illustrated. The results are quite satisfying, and normal distributions could be extracted from that and possibly used in the road generation process. As a last example, I brought the maximum curvature in turning lanes. We see two peaks, which might correspond to left and right turn, since the left turn usually has a wider course in countries with right-hand side traffic. To make use of the extracted parameters from real road networks, we extended the input format and the implementation of the road network generation tool. It is now possible to use random numbers for any value in the input format. A Python command line tool generates concrete templates for the current road generation tool, and as a result, a given number of concrete open drive files is provided. So besides uniform and normal distributions, we can define linear distributions between the variables as well. And as a result of that level, parts of this toolchain will be available on GitHub within this year, I think. And with that, I would like to thank you. And I would have to jump to the next session because I have another presentation, but Andreas and Stefan will gladly answer your questions. If you have questions for me, maybe we can talk in the Wonder Me room later this afternoon. Thank you.
So thank you very much to our speakers, and Daniel, see you later. And now we're going to have a look at the questions the audience might have asked, and I hand over to Frank, who give us some questions what the audience might have asked. Thank you, Frank. Frank, I think you have to unmute yourself. We can't hear you.
No, I just have to put my mic in the right place. So, yeah, so one question already was answered. It was regarding the availability of the open scenario and open drive descriptions. And you already said that during the presentation that you also want to put it online so that it's available for download. As for the use case 2, for instance. And there was another question regarding the tools. There was mentioned a project open or scenario generation for Open Drive. So it seems to be an existing tool which is currently available. Do you know this tool?
I think that would be a question that would refer to Daniel. I think, therefore, maybe you should refer to him in the virtual cafe afterwards.
Okay. So there are no other questions so far. So let me ask a question which could be of interest for the audience. So you're dealing a lot with these scenario descriptions and the existing standards and that stuff, and you compared on the, or you used the measure of lines of code for the descriptions here to give an idea, okay, what is the complexity of an open scenario description? Can you talk a little bit about the expressiveness of open scenario? Is this currently sufficient for the existing use cases you are dealing with, or are there some things missing in the current descriptions?
Okay, I think that like with most of the tools, it's commonly something that is always under development, let's say. What we have seen, for example, is that there was a need to to add properties for describing material properties. This was, for example, something that we have seen that was at the moment not possible. So something like describing the surface in regards to the material that was used. And therefore, we are also considering in the set level project and discussing whether this should be something that could be integrated into the in the open drive format or in the open scenario format, or where the most suitable point for that would be. But yeah, it's basically like with most of the properties, you can always have some additional ideas what you can integrate into these formats. But of course, you have to keep the overview on the standard in a good shape, let's say.
Okay, so because there still is no other questions from the audience, do we have a time for another question?
I think we have time, so if somebody has a question, you can just type it in. And Frank, we're gonna wait like 1 or 2 minutes for questions, and if not, we just move forward to the next presentation.
Okay, let's proceed. So
yeah, so is there anything? Some questions?
Currently not.
Okay, so if you have questions, you can still ask them, and I think we move forward to our second presentation. So thank you very much, Stefan and Andreas, for your answers and your presentation.